Hello, this is Dr. Arnold bringing you another exciting lecture in General Chemistry 1 topics. In this lecture, we'll be looking at practice problems involving gas stoichiometry. So sit back, relax, and enjoy the show. So in gas stoichiometry, somewhere in the stoichiometry process, either at the beginning or at the end, or at both the beginning and end, you're going to need to use the ideal gas equation. So in this example here, we have a reaction involving zinc plus hydrofluoric acid gives us zinc chloride and hydrogen gas. We want to know how many grams of zinc would you need to start with if you wanted to prepare 5 liters of H2 at 350 millimeters of mercury and 30 degrees Celsius. And so here we want to know how many grams of zinc would produce this much hydrogen at this pressure and temperature. And so what we're going to need to do is we're going to take the volume, pressure, temperature of H2, and we're going to convert that to moles of H2, and then using stoichiometry we can convert it to moles of zinc, and then finally mass of zinc. And so that's the process we're going to do. So again, with the ideal gas law, to solve for moles equals, so we got to make sure everything is in the correct units. Pressure needs to be in atmospheres. And try not to round too much. We need to convert temperature into Kelvin. And our volume is in liters already. And of course the R constant. So now we have everything in the right units. We can calculate the moles of hydrogen. Zero 0.09256. So now we know the moles of H2. We can find the moles of zinc. By using the mole ratio. So for every 1 mole of hydrogen, we have 1 mole of zinc. And we get the moles of zinc as well. Now we can find the mass of zinc by multiplying by the molar mass. and we get 6.05 grams of zinc. So this is how many grams are needed to produce 5 liters of hydrogen gas with a pressure at 350 millimeters of mercury at 30 degrees Celsius. In example 2, we want to know the volume of O2 at 15 degrees Celsius and 0.980 atm is produced by the decomposition of 2.36 grams of mercury to oxide. So we want to know what volume of O2 can be produced at this particular temperature and pressure by the decomposition of 2.36 grams of mercury to oxide. So again, you always need a balanced chemical equation. So this is the balanced chemical equation for this decomposition reaction. So now in order to determine the volume of O2, if we want to look at the ideal gas equation, volume of O2 equals the moles of O2 times R times T divided by the pressure of O2. So right now we know what the temperature is, 15 degrees Celsius. We can convert that to Kelvin. The pressure we know it's in atmosphere, so we don't have to convert it, 0.980 atm. And we need to know the moles of O2, and we know what R is. So somehow we have to use the other information to determine what the moles of O2 are. And so the way we're going to find moles of O2 is we're going to take the mass of mercury to oxide, convert it to moles of mercury to oxide, and then we can convert it to moles of O2 using stoichiometry. And once we find the moles of O2, we can then find the volume of O2. And so the molar mass of mercury 2 oxide is 216.6. So we can find the moles of mercury 2 oxide, mass divided by molar mass gives us moles. So that's the moles of mercury 2 oxide. Now we can find the moles of O2 using stoichiometry. For every 2 moles of mercury 2 oxide, we have 1 mole of O2. So now we know the moles of O2, we can calculate the volume of O2. Again, volume of O2 will be in liters. So we get 0.131 liters. Let me double check my work. And so that's the volume of O2 that would be produced. So here in this example, we have a 15-gram sample of aluminum reacts with excess hydrochloric acid to produce aluminum chloride and hydrogen gas. A sample of hydrogen gas was collected over water at 21 degrees Celsius, 540 milliliters of mercury. Calculate the volume of H2 in milliliters collected. And we want to determine, and it gives us the vapor pressure of water is 18.6 millimeters of mercury at 21 degrees Celsius. So here we wanted to determine the volume of H2 collected from this reaction. So again, volume of H2 is going to be the moles of H2 times R times T divided by the pressure of H2. So now we always need a balanced chemical equation. So this is the balanced equation for this reaction. So to find the volume of H2, we need to know the moles of H2, which we don't, the temperature, and in this case it's 21 degrees Celsius. Turn that to Kelvin. The pressure of H2, we don't know, and of course R. And so the moles of H2, what we're going to do is to find the moles of H2, we're going to take the mass of aluminum, convert it to moles of aluminum, convert it to moles of H2. So that's how we find the moles of H2. Now to find the pressure of H2, again, this is collected over water, which means it's a mixture of gases. It's a mixture of water vapor and hydrogen gas. And so that's why it gives us the vapor pressure of water, because this gas that was collected at 540 millimeters of mercury is a mixture of hydrogen and water vapor gas. So again, P total equals P of hydrogen plus P of water. So to find the partial pressure of hydrogen, it would be equal to P total minus the water vapor pressure. And at different temperatures, you have different pressures of water vapor. So partial pressure of hydrogen equals 540 minus 18.6. So now we have that, we can convert it to atmospheres. And so that's the partial pressure of hydrogen that was produced. Now to find the moles of H2. First, we're going to find the moles of aluminum. By dividing by the molar mass. Now we've found the moles of aluminum, we can use stoichiometry to find the moles of H2. So now we've found the moles of H2. We have the pressure of H2, we have the temperature. We can calculate the volume of H2. So we get 29.32 liters. Since it wanted in milliliters, it'd be 29,320 milliliters. We double check the work. All right. So again, anytime you collect a sample of water, now you have a mixture of the gas when the pressure is measured. So it's a mixture of the dry gas and the water. So we have to subtract out the vapor pressure of the water to get the vapor pressure of the dry gas. And this is using Dalton's law of partial pressures. Now this last example, we have 9.45 grams of liquid hexane is introduced into a 10-liter vessel containing 13.15 atmospheres of oxygen gas, and it's at 21 degrees Celsius ignited, and we get carbon dioxide and water. The vessel is then cooled to negative 10 degrees Celsius. What will be the gas pressure inside the vessel? Excuse me. So we need a balanced chemical equation. Now, since it said water and not water vapor, this should be a liquid here. Because in the problem, it said that the water was produced. If it said water vapor, then it would have been gaseous. But since it said water, it would have been, or it is, a liquid. And so we need to find what the gas pressure inside the vessel will be. So the pressure of the total, so the total pressure inside the vessel will equal the total moles of gas inside the vessel times R times T divided by the volume of the vessel. So in order to get and there's different ways you can do this. This is the way I'm going to do it, but there's other ways you can approach this problem. But what I'm going to do is I'm going to find the total moles of gas. Then I can find the total pressure of the gas, because we already know the temperature. Temperature is negative 10 degrees Celsius of the vessel. I should put this as temperature of the vessel. Which is 263 Kelvin. The volume of the vessel, (10 liters). So what we need to know is the total moles of gas in this vessel that we cool down to negative 10 degrees Celsius. And once we find that, we can find the total pressure. So pay attention here, this is a little bit involved. So first off, we have 9.45 grams of liquid hexane produced and is reacted with oxygen gas in a 10-liter vessel at 21 degrees Celsius and 13.15 atmospheres. So what we're going to have to do is we're going to have to take the mass of hexane, convert it to moles of hexane. And again, there's different ways you can approach this. Convert it to moles of CO2. And then also what we're going to do is, that's step one, if you want to call it step one. We do this. Step two, we take the volume, pressure, and temperature of O2, convert it to moles of O2, convert it to moles of CO2. And we want to see which one of these is the limiting reactant. So now pay attention here. If O2 is the limiting reactant, then that makes our job easier because all of O2 will be consumed. The only gas present will be CO2. So if O2 is limiting reactant, excuse me, then P total or N total, so the total moles of gas would just equal the moles of CO2. Now if C6H14 is limiting reactant, then in total, the total moles of gas would equal the moles of CO2 plus moles of excess moles of O2. So that's why we have to determine first which one is a limiting reactant, and then from there we can determine what is going to be the total moles of gas. Is it going to be one gas or a mixture of two gases? So for the first one, converting mass, so we'll find 9.45 grams. We got to multiply it by its, or divide by its molar mass. And then times by the mole ratio. Here it's 12 to 2. And this will give us the how many moles of CO2 is produced by hexane. And we get that many moles of CO2. Now we do the same thing for O2. We determine how many moles of CO2 are produced by O2. And so our volume is 10 liters. Our pressure is already in atmospheres. And temperature needs to be converted to Kelvin. So now we plug these in, we solve for the moles of O2. And so we get the moles of O2 to be 5.448. So now we need to find the moles of CO2 that are produced by the moles of O2. So again, it's a 12 to 19 mole ratio. And we get 3.44 moles of CO2. Let me double check some things. Okay. So we see here that the limiting reactant is hexane. So hexane is the limiting reactant. So since hexane is the limiting reactant, we need the moles of CO2 plus the moles of excess NO2. So we have the moles of O2 total that we start with. So this is the total moles of O2. So if we determine the moles of O2 used, we can determine how many moles of O2 are left over. So the moles of CO2, we know. We get that from the limiting reactant. So moles of CO2 is 0.6593. Now the moles of O2, we first got to determine how many moles of O2 were used. So moles of O2 used equals taking the moles of CO2 and seeing how many moles of O2 were used. and we get this many moles of O2 were used. So now we have the moles of O2 that were used. We have the total moles of O2 that we started with, so we can find out how many moles of O2 are excess. So that would be 5.448 minus 1.0439. And this will give us the moles of O2 in excess. So now we know the moles of O2 that were left over. We know the moles of CO2 that are produced. So now we can determine the total pressure of this mixture, or excuse me, the total moles of this mixture. We get 5.058 moles of gas. So this is the total moles of gas in the mixture. Now that we know the total moles, we can find the total pressure. And we get 10.92 atmospheres. And so that would be the total pressure of this vessel when it's cooled to negative 10 degrees Celsius. Let me just double check my work. Just a slight correction here. This was actually 5.0634. Double check my work. Okay, so that would be the pressure, the total pressure inside the vessel. Once the reaction is complete, the vessel is cooled to -10 degrees Celsius. So again, with gas stoichiometry, either at the beginning or at the end, you'll be using the ideal gas law, or at both end and beginning. So on that note, that's all we have for this lecture. Until next time, Dr. Armand signing off.